So, hello everybody, myself Shomodeep De, your video on Chemical Data. I welcome you all to the YouTube channel of Chemical Data. This is going to be your one-stop solution for all your JEE and NEET chemistry problems. Be it any particular chapter you need to build your concepts on, or problem solving, or previous year questions. We have got it all covered. So, stay connected to ace your preparation for these exams. Okay, so our today's topic of discussion will be a chapter named as chemical bonding. Chemical bonding, where most of us must be knowing, is one of the most important and fundamental chapters of our chemistry syllabus. No matter which level of chemistry we are studying, chemical bonding has always been the most fundamental chapter, mostly because chemical bonding is very conceptual, it is very fundamental, and at the same time, without a sound knowledge of this chapter, moving any further ahead with chemistry, any branch of chemistry with organic, physical, inorganic, is not possible. And also, from point of view of exams, JEE Advanced, Mains, and NEET, or whatever exam you're taking, chemical bonding has a huge weightage of marks. Lots of questions every year are being asked from this chapter. Questions are essentially simple and fundamental. So you guys have a sound knowledge of the concepts. Questions won't be that difficult. So in today's video, we will start this chapter, chemical bonding, and we'll try to cover this chapter in as much detail as possible so that your concept of this chapter is crystal clear and you are able to solve any question, be it previous year or upcoming questions in whatever exams you guys are having. Okay. So let's get started. And also one more thing, before we begin with this chapter, guys need to have a sound idea of two more chapters, one being atomic structure and the second one being periodic table. So if you guys don't have a basic idea of this chapter, it's advisable to go and do the chapters first, go through the NCRT, build a fundamental idea, then come and study chemical bonding. And also don't get worried, we will be covering these two chapters in the upcoming videos. But as for now, let's concentrate on chemical bonding. So, chemical bond is a very simple thing that we have been studying since our junior classes. Is a bond that connects two chemical species together, say A and B, together in a stable molecule. In a stable molecule. This is what a chemical bond is. Like, be it the pen that I'm using to write on, or the piece of paper that you're scribbling on, or the life-saving water that we have. All of them have got chemical bonds. All of them have got chemical bonds. So, chemical bond can be fundamentally divided into two categories, two very basic categories. Strong bond and the weaker bond. Now, in the category of strong bonds, we'll be discussing mostly about the ionic bond, which we also known as the electrovalent bond, sometimes electrovalent bond, also the covalent bond, and to some extent the metallic bond. As for the examination point of view, the ionic bond and the covalent bond, these two are the most important types of bonding characteristics. These two are the ones we need to focus the most on, and questions are asked from these two mostly. Metallic bond, yes, to some extent, yes, but they're not that common. Now, moving over to weaker bonds. Weaker bonds are mostly consisting of van der Waals force of interaction, named after the scientist Van der Waal. Van der Waal. And secondly, hydrogen bonding. Now, hydrogen bonding is just to give an idea, hydrogen bonding is not any separate kind of bonding interaction. It is just a special case of van der Waals force of interaction. But just because hydrogen bonding plays a very important role in our day-to-day life and like the body of humans and any other animals, we tend to study it as a different bonding interaction, but mostly it's a special type of van der Waals force of interaction. Okay, so let's get some idea about the ionic bond. So ionic bond, I guess every one of you has got some idea about from the junior classes. We will discuss about this in upcoming chapters, but as for now, let's get some idea about the ionic bond. An ionic bond is essentially formed between two species, a cation and an anion. A cation is formed when a species loses an electron, and an anion is formed when a species gains an electron, gains one or more electrons. So we already know from our junior classes that two different charges attract each other, or A plus and B minus, they attract each other. They form a bond between A and B. It is basically an electrostatic force of interaction. A and B. Done. Okay. Now moving on. So this is this much for the ionic bond. For now, we will know more about it in the upcoming videos. Now moving on to covalent bonding now. Covalent bond. Covalent bond is just the opposite of ionic bond. In ionic bond, we have seen how A forms a cation, say for example, sodium going to sodium plus and chlorine coming to Cl minus. Both of them combine to give you the table salt sodium chloride or NaCl. However, in covalent bond, there is no such ion formation. It is mostly or almost always, or rather always, sharing of electrons. Sharing of electrons. Only sharing of electrons. And the most common example is, I guess, water. Because without this, life is impossible. So, water, I think, is going to be the most fundamental example of a compound having covalent bonds between oxygen and hydrogen. Okay, now one more thing. I also think that guys have some idea about the octet rule. Do we know what the octet rule is? If we don't, just to give you a basic idea what it is. The octet rule says any atom tends to form as many bonds as needed so as to have 8 valence electrons. What do I mean by that? See, an atom can an atom can form a one bond, it can form two bonds, three bonds, four bonds, six bonds, whatever it needs to. But it will form just the number of bonds it needs so that we have got 8 electrons in the valence shell. 8 electrons in the valence shell. As an example, let's take water again. Let's take water again. What is water? It's H2O. So we have two hydrogen and one oxygen. Oxygen, we know from the atomic structure chapter, it has got 6 electrons in the valence shell. It is 1s2, 2s2, and 2p4. It talks about the valence electrons, so we'll talk only about the valence electrons here. Let's see what they have got in store for us. 2s2 and 2p4, something like this. I hope we are all aware of this, how to write the electronic configuration. So oxygen we can see has got 6 valence electrons, Ve as I would write them in short. 6 valence electrons. So it is 2 electrons short of 8 electrons in valence shell. So it needs 2 electrons. This is the reason why the valency of oxygen is 2 minus. It always tends to accept 2 electrons, 1 electron here and 1 electron here. So it always tends to accept 2 electrons. So the valency of oxygen is always -2. This is what octet rule tells us. Understood? So talking about water, there is another rule called the duplet rule. Called the duplet rule. This is applicable mostly or maybe always for hydrogen. This rule says that it like just like the octet rule says 8 electrons in the valence shell, The duplet rule says two electrons in the first and final shell. First and final shell. That is, there should be only one shell, which is the first shell, and which is the final shell as well, and there must be two electrons in them. Say, for example, hydrogen. Hydrogen is the simplest atom possible, 1s1. So it's got only one electron in its valence shell, which is also the first shell. So, in order for a hydrogen to be stable, it needs to have one more electron in the valence shell, which will make it H2. Like one hydrogen combines with another hydrogen to give you H2. Coming to water now, the water molecule. See, look at this. It will clear all your problems about the covalent bonding, about the concept of electron sharing. Oxygen, if we just write the valence shell configuration, 2s2 and 2p4. So it needs two electrons. Hydrogen comes. Hydrogen needs one electron, mind it. Each hydrogen needs one electron. In the water molecule, we have two hydrogen and one oxygen. And each hydrogen needs one electron in order to get the octet, I mean the duplet complete, sorry. Hydrogen has got one electron which it donates here. Another hydrogen comes with another electron which is donated here. So it looks something like this. Oxygen was having six electrons initially, something like this, one, two, three, four, five, and six. And then hydrogen comes in from somewhere in the middle with one electron here and one electron here. I've used a different color for hydrogen electron so that it's visible. Red for hydrogen now. Okay, these two electrons they combine. These two electrons they combine. Now, to give you a very like layman example, suppose your mom comes and gives you a piece of chocolate and asks you to share the chocolate with your younger sibling. Willing or unwilling, you have to share the chocolate with your brother or your sister. Sorry. So you share the chocolate with your sibling. Then what happens? The chocolate is just as much your as it is of your younger sibling. So you can call the chocolate yours, and your sibling can also call the chocolate his or her because it is now shared between the two of you. The same case, I'm saying the same case, exactly the same case is applicable here. This electron, the one in red, initially belongs to hydrogen. This electron, somewhat in a lighter color, maybe lighter shade of pink, earlier used to belong to oxygen. However, now these two electrons combine like they are shared. Now this electron, the one in red, belongs to hydrogen just as much as it belongs to oxygen. This electron in pink belongs to hydrogen just as much as it belongs to oxygen. That is, how many electrons does oxygen have now? One, two, three, four, five, six, is also counted, seven, and eight. So oxygen is now having eight electrons in the valence shell. So the octet rule is complete. Coming to hydrogen now. Hydrogen, it had one electron. No, no, no. It's got two now. One from this one as well. So hydrogen has got two electrons. This one also got two electrons. Hydrogen having two electrons in the valence shell, thus completing its duplet rule, and thus it is extremely, extremely stable. In this case, oxygen has a complete octet, hydrogen has a complete duplet. So the water molecule is extremely stable, extremely stable. Okay, okay, one more example of the covalent bonding. Say, for example, the methane molecule, CH4. Now, carbon has got four valence electrons. Carbon has got four valence electrons. How do we draw it? Carbon, one, two, three, and four. Fine. Okay. Now, carbon has got four electrons, so it is four electron short of octet. Four electron short of octet. So it needs four more electrons. So what it does, it forms four bonds with hydrogens. One bond here, one bond here, one here, and one here as well. So what do we have at the end of the game? At the end of the game, we have these two electrons combining. I think the color is not visible properly. Okay, so these two electrons combine, these two, and then these two combine. Like I've already said, now every electron belongs to every molecule since it is shared now. You can't say that carbon's green electron belongs to carbon now. No. Carbon's green electron is as much as it is of carbon, as much as it is of hydrogen now. So carbon has now got how many electrons? One, 2, 3, 4, 5, 6, and 7, 8 electrons. And hydrogen, like each one of them, have got two electrons. One, two, one, two, one, two, and one, two. So hydrogen has got a duplet complete, and carbon got an octet complete. So the CH3 molecule, CH4 molecule, sorry, is extremely stable. Extremely stable. Understood? This is the octet rule. Now, there is an exception to the octet rule. Now, as for me, I have a problem with the name octet rule because a rule is something that you should not violate. Traffic rules you should not violate. Penal rules you should not violate. So no rule should you violate. However, this octet rule we'll see now is often violated. That is an octet rule. We can't call it a rule to be specific. It's mostly a generalization. A generalization. Generalization. How? How? See, human beings have this tendency of whatever they see happening most of the time, they make it as a rule. Like mostly in our social structure, whenever a thing happens for a lot of time, we tend to make that as a rule. Similarly, octet rule is not a rule. Octet not a rule. It's a strong statement I'm making. It's a generalization. It's simply a generalization. We will see how. Say, for example, the molecule BH3. BH3. So it has got boron and three hydrogen in it. What is boron? Let's look at boron once. Boron is 1s2, 2s2, 2p1. So boron has now got three electrons in the valence shell. Three electrons in the valence shell. Fine. So it looks something like this. So you excite one electron to this orbital. I hope guys have got some idea about the electron excitation. It's from the chapter periodic table. Okay, we'll discuss about it in some detail. See, boron has got two electrons here, and boron needs to form three. See, look at this molecule. Look at the molecule first. The molecule is BH3. That is boron and three hydrogen they combine. One boron and three hydrogen they combine. That is boron is forming three bonds. Now to form a bond, you need one electron. And to form three bonds, you will need three electrons. Three electrons. Boron will need to have three electrons. However, in this case, boron seems to have only one unpaired electron. So what can we do? We can excite one electron from the 2s to the 2p. How do we do that? It's pretty simple. Not so simple in the laboratory, but it's simple in a piece of pen and paper. So you can do what? You can supply some energy. You can supply some amount of energy to excite the electron from 2s to 2p. It now looks something like this. Fine. So we can now justify three valence electrons ready to form bonds. In this case, there's only one valence electron ready to form a bond. And in this case, after we excite the electron, we have got three electrons ready to form a bond each. Okay. Now, we have got three hydrogens. Let's bring the hydrogens one by one. One hydrogen forms a bond here, another hydrogen forms a bond here, another one forms a bond here. Now let's look at the Lewis dot structure. Remember, these structure are called the Lewis dot structure. Lewis, a scientist, gave the idea of drawing molecular structures like these, where you represent the electrons as dots. Okay, so let's look at this thing now. It is boron, one electron each on three sides will make three electrons, and hydrogen comes along with one electron each, forming a bond for three hydrogens. Okay, now guys tell me, it's very much visible. How many bonds, how many electrons does boron have now in the valence shell? Two from here, two from here, two from here. Like I told you, after sharing, every electron belongs to every other species. So you can't say that this green electron belongs to boron, not to hydrogen, or the blue ones belongs to hydrogen and not to boron. No, each of them belong to everybody. So we have got two electrons here. So boron has got six electron in the valence shell. Hydrogen has got two electrons though, one, two, one, two, one, two. So hydrogen has got two electrons. So it is satisfying the duplet rule. No issues with that, and we're not concerned about the duplet rule as well. We're talking about the octet rule not being a rule and more of a generalization. Why so? Because boron has now got six electrons in the valence shell, which is two electron short of the octet rule That is, the octet rule is violated. Octet rule violated. Oh my, what did I write here? Octet rule is violated. What does this mean? Does this mean that the molecule BH3 is not stable? It should mean so. It must imply this, that since boron is not following the octet rule, BH3 should not be stable. It should be unstable. But is it so? Of course not. Of course not. It is very much stable. This molecule is very much stable. That is, molecules can be stable even when they don't follow the octet rule. This very easily and very clearly shows that octet rule is never a rule, or rather a generalization, because we see 90% or maybe a bit more, I won't comment on the exact figure, like most of the molecules, most of the atoms, they tend to have eight electrons in the valence shell and then form a stable molecule. We tend to call octet rule a rule as such. But we can see from this example, it's very clear that even when you have less than eight electrons, you can form a very much stable molecule. And these molecules are called hypovalent molecules. Please keep this term in mind. Please keep this term in mind. It is a very common thing for JEE mains and NEET. Not so much for advanced, but this term hypovalent is very important. You're often given like four options and you're asked to pick out the hypovalent molecule. So how do you do that? You see which molecule has got less than eight electrons, like for the central atom, in this case boron. You see which central atom has got less than eight electrons and you call that hypovalent. Okay. Similarly, you got the hypovalent where you have got less than eight electrons. There must be a case where you have got more than eight electrons. Yes, you heard me right. This is also possible, and you call this hypervalent. You call this hypervalent molecule, more than eight electrons. And now that we have spoken of this, let's take an example as well. PCl5. PCl5. Okay, so phosphorus is 3s2, 3p3, and 3d0. So phosphorus in this case, in this molecule, is forming five bonds. And to form five bonds, you need five unpaired electrons. You need five unpaired electrons. Now, how do you make that? How do you make that? Let's have a look at this thing now. 3s2, 3p3, and 3d0. But how many unpaired electrons do you have in this case? One, two, and three. But on the contrary, as the molecule says, you need five unpaired electrons. How do you do that? Just in the previous case, we saw supply energy, excite the electron. Supply energy, excite the electron. So what do you see? What do you see in this case? You see something very simple. One electron, these are untouched, and one electron comes to 3D. We have got one here. Now, how many unpaired electrons do we have? One, two, three, four, and five. Now, five unpaired electrons ready to form five bonds. Chlorine we know has got seven electrons in the valence shell. So the valency of chlorine is one. Like, okay, let's show for you guys what chlorine actually looks like. It's 3s2, 3p5. That is seven electrons in the valence shell. So it is just one electron short of forming a complete octet. Like this electron, if it pairs up with somebody else, we will have eight electrons. One, two, three, four, five, six, seven, eight. So chlorine needs one electron, and this one electron is supplied by phosphorus. See, chlorine, 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 and yet another chlorine. So what do we have here? Please see. Chlorine has got now, it had seven electrons of itself and one electron. This one, it comes from phosphorus. So chlorine has now got one, two, three, four, five, six, seven, and eight electrons. So chlorine has got a complete octet. Excellent, fine, extraordinary. However, let's have a look at phosphorus. It is having how many electrons? Phosphorus is having now two, 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 two. That makes it 10. Phosphorus having one, two, three, four, and five electrons, and they are forming bond with chlorine, 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 and chlorine. Now, if we can draw the circle, the Lewis dot structure will be complete now. So now phosphorus has got how many electrons? Two, 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 two. Phosphorus has now got 10 electrons. 10 electrons, which is way more than 8 electrons. That is the octet rule is again violated. Octet violated. That is a rule which is violated every other time. You can't call that a rule as such. People or molecules not paying much importance to octet nowadays. So these kind of molecules having more than eight electrons are in their valence shell are called hypervalent molecules, as I've already mentioned. Hypervalent molecules. So what is the actual thing behind this? So again, questions are very common in JEE mains, mostly NEET, not so much in JEE advanced about the hypervalent and the hypovalent molecules. Now the actual thing is that every atom tends to pair up all its electrons, tends to pair up all its valence electrons. Once all the valence electrons are paired up, the system is stable. Once all the valence electrons are paired up, the system is stable. I've said a very important thing here. Once all the valence electrons are pair up all the valence electron, system is stable. Let's have an example of this. Let's look at this molecule now. The ammonia molecule or the NH3 molecule. What does nitrogen look like? Nitrogen look like 2s2, 2p3, and there is no 2d orbital for sure. To something like this. So, let's look at nitrogen now. It has got no 2D, no 2D. It's not. not there. So you can't possibly excite this electron like we have been doing case of phosphorus and boron. You can't do this. You can't excite this electron to have any extra unpaired electrons. So in all the cases, nitrogen will have three unpaired electrons, no matter what the case is. It will always have three unpaired electrons. Because see, these two electrons are paired up. These two electrons are paired up. And we have been talking about pairing up the valence shell electrons. And since the electrons are already paired up among themselves, you don't need to worry about somebody else coming from outside and forming a bond with these electrons because these are already paired up. You need to pair these three up. These three can be paired with one electron of hydrogen, one electron of hydrogen, and one electron of hydrogen. In this case, you see hydrogen has a duplet now. Fine, it's always happy hydrogen. Let's have a look at nitrogen now. One, two, three, four, five, six, seven, eight. Nitrogen has now got 8 electrons or a complete octet or complete octet. That is, all the atom or the element wants is to pair up all the electrons, is to pair up all the electrons. That's all you want to pair up all the electrons. Now, in this process of pairing up all the electrons, most of the elements, mostly they end up having 8 valence electrons. They end up having 8 valence electrons, and people have generalized this thing as something called the octet rule. But this is not a rule, it is just a generalization. Now, to give you yet another and the final example of today's class, we will talk about a molecule called PF3. PF3. Now, fluorine, as we know, is a halogen and has got one unpaired electron. One unpaired electron, and it looks something like this: 2s2, 2p5. So, fluorine is having one unpaired electron in its 2p orbital. Look at this. So 1, 2, 3, 4, 5, 6, and 7. It has got 7 electrons, 1 electron short of octet. And let's look at fluorine phosphorus now. Phosphorus we know is 3s2, 3p3, and 3d0. So you can draw it like this, okay, and 3d0 like this. Now, if you look at this molecule now, PF3, you can very well see that phosphorus is forming bond with three fluorine atoms. With three fluorine atoms. Now to form three bonds, you need three electrons, or rather three electrons unpaired, three electrons unpaired. Now phosphorus in its ground state has already got three unpaired electrons. Tell me now, do we need to supply any energy? Do we need to supply any energy? I don't think so. We need to, because if we supply the energy, this electron will come up to the 3d orbital and will give you five unpaired electrons, as in the previous case of PCl5 we discussed. But in that case we needed 5 electrons. That's why we supplied the energy to excite the electron. But in this case we need only 3 electrons, and believe me, energy is not cheap in today's date. Energy is not cheap. So better not spend energy over things that are not needed. We need 3 electrons. Phosphorus already got 3 electrons. So you can very well do it like this. 3s2, like the 3s. This is the 3p orbital that I will be drawing here. The 3p orbital, 1, 2, and 3. And fluorine comes along with its 1 electron, forms a bond, 1 electron, forms a bond, 1 electron, forms a bond. And for fluorine got its complete octets, complete. Phosphorus also has got 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. In this case, phosphorus does follow the octet rule. In the molecule PCl5, if we just scroll up a few more pages, maybe one or two, we will see that phosphorus in this case is having 10 electrons. Having 10, as I wrote here. in big numbers 10 electrons. So there is no generalization, there is no any sort of hard and fast rule. You get as many electrons as the number of bonds you form. In this case, PCl5 fluorine needed to form 5 bonds. That is why we had to excite the electron, and in the process, we got 10 electrons in the system. However, in case of PF5, we don't need to form any more than 3 bonds. We form 3 bonds, and in the process, we don't need to give any extra energy. And this formation is not needed. This is enough, and we end up having 8 electrons. And if you also see, we have paired up all the valence electrons. 3 electrons in 3p are paired up with 1 fluorine each, and the 2 electrons in the 3s orbital are paired up among themselves. So this very well proves the fact that all we need is to pair up the valence electrons, is to pair up the valence electron, be it with themselves, like among themselves, or somebody else, or somebody else. All we need to do, all we need to do is just to pair the electrons up. Done. So this is what we have discussed so far, the octet rule, or maybe not a rule so much, maybe just a generalization of a few facts combined together, and the hypovalent and the hypervalent molecules. So that's all for now. See you again in the next video with some more concepts of chemical bonding. We'll come back and try to solve some more questions and solve some more doubts. So as for now, thank you. Stay connected, subscribe to my channel for more such videos, and happy learning. Thank you.